This video is for Chemistry in the Earth System, Unit 2.2, Arrangement of Electrons in the Atom. Our first essential question today, what arrangement of electrons in an atom did Niels Bohr propose? First main idea, Rutherford's nucleus. At the turn of the 20th century, understanding the structure of the atom was one of the most sought-after goals in physics. In 1897, J.J. Thomson discovered the electron and proposed his plum-pudding model of the atom.
In time, evidence began to emerge suggesting that atoms are made up of even smaller particles called the electron, proton, and neutron. The discovery of these particles makes an interesting story.
J.J. Thomson, an English scientist, discovered the electron, the first of these particles, in 1897. Electrons are particles which are smaller than atoms and which have a negative charge. Thomson knew that atoms themselves were neutral in charge, but he couldn't find the positive particles that would balance the negative charges of the electrons. It took other scientists to discover them.
So, a few years later, Ernest Rutherford challenged Thomson's model. Rutherford's experiments led him to conclude that the atom must have a nucleus. Rutherford proposed that an atom's mass is concentrated at its center. Protons and neutrons had not yet been discovered, so Rutherford could not tell what the nucleus of an atom is made of. Rutherford was also unable to determine the arrangement of electrons in the atom. He suggested that the electrons move in orbits around the nucleus, but he had no evidence to support this hypothesis. Indeed, the idea of orbiting electrons was poorly received by physicists at the time because it did not agree with the laws of classical mechanics developed by Isaac Newton. Because according to these laws, orbiting electrons would continually lose energy and eventually fall into the nucleus. Since this obviously did not happen, Rutherford's hypothesis was rejected.
In 1911, Ernest Rutherford added more to our understanding of the atom. He fired a stream of positively charged particles at a thin sheet of gold foil. He found that most particles passed right through the gold atoms in the sheet of foil. He concluded that the atoms were mostly made of space. Some particles, however, were deflected by the gold foil. He concluded that the atom had a small, dense, positively charged center that repelled the positively charged bullets. He called the center of the atom the nucleus. The nucleus is very tiny compared to the atom as a whole, equivalent in ratio to a marble in a stadium. Rutherford stated that all of an atom's positively charged particles were in the nucleus, and negatively charged particles were scattered outside the nucleus around the perimeter of the atom.
Our next main idea, light-emitting atoms. Niels Bohr joined Rutherford's lab in 1912 to study the arrangement of electrons in atoms. Bohr's careful research led him to propose a model of electron orbits that satisfied both experimental evidence and those laws of physics that we described earlier. When Niels Bohr began his work, several observations of atomic behavior had not yet been explained. One set of observations concerned the way that atoms emit light. Scientists had observed that different elements emit different wavelengths of light. These wavelengths are seen as colors of light emitted when elements are heated or when electric current is passed through them. Neon gas, for example, emits red light when an electric current passes through it. Xenon gas produces blue light. The colors emitted by elements are called emission spectra. Each element has a specific emission spectrum. Each element also absorbs wavelengths of light, the pattern of which is called the absorption spectrum. The emission and absorption spectra of hydrogen were of great interest to scientists at the time Bohr began working in Rutherford's lab. Bohr used spectroscopic observations of hydrogen and other pieces of experimental evidence to guide his research. Bohr discovered that the specific pattern of light emitted and absorbed by different elements is connected to the arrangement of electrons in their atom. Our next main idea, Bohr's model of electron arrangement. Bohr proposed that the light-related behavior of atoms was due to electrons traveling at specific energy levels in fixed paths around the nucleus. Electrons at each energy level had a fixed amount of energy. Electrons remain in their energy levels unless something causes them to move to a different energy level. Bohr showed that when an electron moves from a higher energy level to a lower one, it emits energy. The specific amount is equal to the difference in energy between the two levels. This energy is emitted in the form of light. The color or wavelength of the light emitted is related to its amount of energy. Conversely, for an electron to move from a lower energy level to a higher one, it must absorb energy. The amount it absorbs is equal to the energy difference between the levels. The wavelength that is absorbed is also related to this amount of energy. Bohr called the specific amounts of energy emitted or absorbed by electrons moving between energy levels a quantum of energy. Our next main idea, Bohr's calculations. Bohr used mathematics to show how his model explained the emission spectrum of hydrogen. He calculated the energy of a hydrogen electron using the equation here. The energy, represented by E, is the energy of an electron, and N is an integer that corresponds to the energy level where the electron is located. When Bohr applied this equation to determine the energy levels of the hydrogen atom, he found that the values matched those predicted by hydrogen's emission spectrum. This meant that his model could explain the observed behavior of hydrogen. Let's take a look at a sample problem. Calculate the energy of an electron in the fourth energy level, which is N is equal to 4, of hydrogen. So, how would we do this? Recall that the equation relating energy and energy level is E is equal to negative 2.178 times 10 to the negative 18th joules, all multiplied by the inverse of N squared. To calculate E, substitute the value of 4 for N, and then solve, according to the steps on the screen here. Note that the energy has a negative sign associated with it. This is because E approaches 0 as N gets larger. Thus, an electron far away from the nucleus has essentially 0 energy. Its energy becomes more negative as the electron moves toward the nucleus. Our last main idea, limitations of the Bohr model. Bohr's model fit only data related to hydrogen atoms. It could not be used to calculate energy levels in other elements, meaning elements that had more than one electron. This shortcoming prompted other physicists to continue unraveling the mysteries of atomic structure. Although the Bohr model was useful only for the hydrogen atom, it marked an important milestone in atomic physics. The Bohr model made it clear that the electron shells in an atom were quantized or related to specific amounts or quantities of energy. The emission and absorption of light by atoms could be explained by assuming the electrons gain or lose specific quantities of energy when they move from one energy level to another. At this point, you should be able to generate a full and appropriate response to today's essential question. What arrangement of electrons in an atom did Niels Bohr propose?